Welcome, everybody. I'm David Bader, and I direct New Jersey Institute of Technology's Institute for Data Science. I want to welcome you to this week's Data Science Seminar, everyone who's here with us on Zoom or following us on our YouTube channel. We have a great speaker for you this week. Adam McLaughlin is a research scientist at D.E. Shaw Research, working on embedded software and hardware verification for Anton, a massively parallel supercomputer used for fast simulation of molecular dynamics for drug discovery projects and fundamental biochemistry research. I'm especially proud today because Adam did his doctorate under my direction, and during that time, Adam worked on accelerating graph algorithms using GPUs. And this talk is based on one of those papers that was a best student paper finalist at the 2014 Supercomputing, or SC, conference, and later a research highlight in communications of the ACM. Adam enjoys concerts, comedy shows, and he reminisces about his previous days as a semi-professional poker player. So I'm really pleased to introduce Adam to you today.
Thanks, David. Thank you very much, David, for the introduction. As David said, I currently work at D.E. Shaw Research, but today I'm going to talk about some work I did while I was at Georgia Tech doing a doctorate under him. So the title of the seminal paper for this work is called Scalable and High Performance Betweenness Centrality on the GPU. There we go. So there's a lot of applications of interest that people in the computer science community are dedicated toward solving. So there's problems in computational biology, social network analysis, urban planning, et cetera. And while these particular fields don't seem to have too much in common, when you're applying some computer science concepts to them, one thing that falls under all these problems is that you can use graph analysis to tackle them. So graphs are a nice general way to express data that can apply to all sorts of domains. But what you receive for that convenience of being able to apply to all sorts of domains, you also receive challenges in processing graphs. So in particular, graphs that are of interest are particularly large. So there's no chance they can be manually inspected, and you need robust algorithms that scale to, millions, if not billions, of vertices. Graphs are also unique in that they have varying structural properties, and many graphs can have some similar characteristics to them, even quantitative characteristics, but actually look quite different. So there's this so-called small world phenomenon. There are scale-free graphs. There are meshes, road networks. So graphs aren't this one-size-fits-all problem, and you're going to need potentially different techniques to apply to different types of graphs, which we'll get into later. Finally, graphs are unpredictable. They're not a clean n by n matrix where you have predictable memory access patterns. Nodes can have any number of connections to them, and that leads to challenges when creating graph algorithms. In addition, this work also focuses on GPU computing, which has its own challenges. So GPU computing has generic parallel programming challenges that you would also see when computing things on an ASIC or a parallel CPU, like deadlock, synchronization, race conditions, and things like that. But they also have challenges that are specific to GPU computing, such as architectural and ecosystem challenges. And admittedly, this has gotten better over the years, but I still think this is an issue with the GPU computing community, particularly in that you have to have a very fundamentally deep understanding of the architecture if you want to eke out any bit of performance. So you really need to know about how threads operate in lockstep. You have to be able to manage programmer accessible shared memory instead of being able to rely on a cache and a CPU, things like that. But like I said, this is getting better because things like Thrust, which is now a library that's essentially been integrated into the C++ standard, are making these sort of very low-level primitives more easily accessible to programmers who might not be domain experts in GPU computing. So that's kind of a setup of the motivation of the problems we're trying to solve. So let's talk about a metric that we can use to help solve these problems. And that metric that we're going to focus on today is called betweenness centrality. So betweenness centrality is just trying to figure out the relative ranking of vertices in a network in terms of importance. Where importance here really means how many the easiest way for information to flow from one end of the network to the other. And we'll get into a more explicit definition of what betweenness centrality is, but for now, you can just think that it requires a solution of the all pairs shortest path problem. And the picture on the right, you can see the vertices on the kind of edge ring here are in red, are like the least important. And then the vertices that are in dark blue and green here are much more important, and like the vertices in yellow are in between. So it gives you some notion of, in this case, what's physically central in the picture, but what it's trying to measure is, how central a vertex is in order, in terms of flow from one side of the graph to the other for the entire graph. There are tons of applications of this, so it's not a contrived example. In particular, community detection is a really good example. So trying to break up social networks into different communities for further analysis, betweenness centrality is an excellent algorithm to build on for those sorts of things. But like I said, it requires a solution of the all pair shortest path problem. So it's pretty computationally demanding. For a graph with n vertices and m edges, it requires order mn time complexity, which scales pretty poorly when you get to larger graphs. So let's just go ahead and formally define it. I promise not to put up too much math here, but it's useful to kind of get an equation and an example to go with it. So I went ahead and added the slide. So formally, if you want to look at the betweenness centrality of a vertex V, you can take it as a summation for all vertices S and T that are not equal to V of this sigma S of T V over sigma S of T, where the denominator here is the number of shortest paths from S to T, and sigma S of T of V in the numerator is the number of those such paths that pass through V. So in a very simple example here, I have a graph with vertices S, U, T, and V. So sigma S of T is the number of shortest paths from S to T. There's one that goes through V, another goes through U, so there's two of them. So sigma S of T is 2. Of those paths, only one of them passes through the vertex V, so sigma S of T of V is 1. And then symmetrically, sigma S of T of U would also be 1 because there's one of those such paths that crosses through U. Here's an example of a graph with actual betweenness centrality scores on it, just to give some semblance and like kind of quantify the importance of this sort of metric and how things look numerically. Even going through a graph this small and like trying to enumerate every single calculation would actually be pretty cumbersome and take a lot of time. So I won't bother to do that here. But what I do want to point out is there is some intuition about the numbers here. So there's a few vertices that have a betweenness centrality score of 0. So vertex 9, vertex 8, vertex 2. That's because no shortest paths from any other two vertices need to go through that vertex. So in other words, if you want to get from 3 to 1, you don't need to get through 2, 3 to 4, 1 to 4, or any other combination of vertices. You never have to pass through 2 to get to those vertices on a quick path. And you could do the same intuition for the other vertices with score 0. And naturally in this graph, it's pretty obvious that 4 would have the highest score because it's pretty central from anything on this left-hand side to anything on this right-hand side. One thing that I should note is that the actual absolute values of the scores here are less important. What's more important is the relative ranking of betweenness centrality scores between vertices. So what you might care about in this particular graph is that 4 is the most important vertex, followed by the 7 and 5, and 6, for instance. So I've kind of gone through, applications we're interested in, a metric for helping us solve problems in those applications. So now let's talk about an algorithm for computing that metric. And this is where most of the work will come in. So Betweenness' algorithm is the kind of best known algorithm for computing betweenness centrality. And we can break it up into 2 parts, both of which are order mn complexity. So the whole algorithm is the same complexity. First is called the shortest path calculation, which is basically starting a breadth first search and calculating all the shortest paths from one particular source vertex to all the other vertices downstream from it. And then there's a dependency accumulation, which is starting at the other side of the graph and moving your way back up to that root vertex that you started from. So basically, there's a way we can redefine the equation on the other side I showed in terms of this dependency. And what that does is it formulates everything in terms of the successors of a given vertex, which lets you basically go back up the graph the same way you came down, and the opposite way you came down, which makes it algorithmically much easier to calculate BC. So you can calculate the betweenness centrality now. It's just the summation of delta SV. So let's talk about some existing work here and how we're going to build upon it. So there's a few existing GPU implementations of betweenness centrality before the work that I'll discuss that we improve upon. So first is just by Jai et al. It was in the GPU Gems book, which is like one of those first fundamental books that came out when GPU computing for generic applications became a thing. So they have a couple of different parallel methods that we'll also go into. Some, better utilize the GPU. And then there was GPU fan not too long later that showed a small speed up over them, but the results were kind of limited in scope. So I decided to compare our results to both of these packages. But they both have some flaws, which we're gonna, try and take advantage of and correct and improve upon. First is that they use these large predecessor arrays, which are order m or order n squared in size, which we don't actually need at all. So if you're keeping an explicit queue of vertices, you in fact don't even need this array. So that just reduces the memory bandwidth required by the algorithm. And they both also use order n squared graph traversals because they happen to check every vertex or every edge of the graph, depending on exactly what implementation you're looking at. And in general, obviously that's bad because you can do a breadth first search much faster than that. But in terms of maximizing the memory bandwidth of the GPU, sometimes it's admissible to use a slower algorithm because it'll actually use more memory bandwidth and compute things faster in practice. So what our approach will do is actually figure out when that occurs and take advantage of it. So let me go into what we did here and how it's similar and different to the approaches that I just explained. So one thing that's similar to both of those approaches is the coarse grain parallelization strategy. So to those of you who might not be familiar with GPU programming, you can think of a GPU as a set of a bunch of parallel processors that are called streaming multiprocessors. So I kind of have this CUDA grid here. You can think of like, one GPU. And then you can think of these SMs as different computing units that are parallel within that GPU. And then within each of those SMs, there are threads that are also parallel. So there's kind of like this hierarchy of parallelism here. You have the overall GPU, each streaming multiprocessor within the GPU, and a parallel number of those, and then parallel threads within each multiprocessor. So that's actually pretty nice for the betweenness centrality algorithm because it leads to a natural decomposition of work. So since we need to solve the all pair shortest path problem, what we essentially need to do first is start a breadth first search from every single node in our input graph. And since those searches are independent, we can assign them to each streaming multiprocessor. So, let's say this is our graph here. We'll give SM0, and we'll let that start from vertex 1, and then SM1 can start from vertex 2, et cetera, until your final SM will work on the final vertex. Of course, in practice, the graphs will be much larger than the number of streaming multiprocessors. The number of streaming multiprocessors on a typical GPU these days are, in order, 50. So clearly you'll have more nodes than that. So you just, loop over the streaming multiprocessors and they'll handle multiple breadth first searches sequentially per multiprocessor, but parallel among the multiprocessors. So I'll go into this in more detail, but within each streaming multiprocessor, you're going to start from its assigned root vertex, do your breadth first search down the graph, do your dependency accumulation up the graph. And what that'll give you is some local modifications to your betweenness centrality scores. And then all you need to do is do some sort of reduction or atomic add. It doesn't really matter. Well, it does matter that it's atomic or it's done in parallel safely. And then you'll have global updates to the betweenness centrality scores for the whole graph once that's all done. So the more interesting topic to talk about, as the last part was kind of embarrassingly parallel, is the fine grained parallelization strategy. So I'll first talk about some of the methods used by previous work, and then I'll explain how we improve upon those methods. So first of all, there's a vertex downward traversal, which was from the GPU gems example that I mentioned before. So this is basically just trying to do a breadth first search and compute shortest paths. And the way it works is that it'll assign one thread to every vertex in the graph. So let's say we're traversing from source vertex 1 here. It has 3 edges, so it'll assign a thread to every vertex, and most of these threads will do nothing, right? So the thread that's on vertex 6 is not active right now. It doesn't need to do any work. Same thing for every thread except the one on vertex 1. So there's a lot of wasted work there because threads are just being assigned for essentially no reason. And then additionally, you have the issue here that vertex 1 has to do the thread on vertex 1 has to traverse 3 edges. And you can imagine for graphs in general, if I move to the next stage here, you're going to have now vertex 2 is processing 2 edges, vertex 3 is processing 3 edges, vertex 4 is processing 4 edges. And in general, those numbers can be arbitrarily different. So you could have a massive load imbalance because you have one thread here that's doing 4 pieces of work and another thread here that's doing 2 pieces of work. Well, for a scale-free graph, that could be 1,000,000 to 1 or even worse. So you have this massive critical path for the thread that has the largest amount of work. So there's a few, it's an easy way to write up. There's something wrong with it, but it's not the most efficient way. So those authors of the same paper also came up with an edge parallel method. So in this case, instead of assigning a thread to every vertex, you're now going to assign a thread to every edge. So this has the advantage that even if for a scale-free graph, you have one vertex that has lots of neighbors and another vertex that doesn't have a lot of neighbors, well, you're assigning threads to edges now, so you don't care about that. So the work that needs to be done will be evenly distributed. The problem is, the disadvantage here is that there are typically much more edges in the graph than nodes, especially in practice. So you have even more threads now that are looking at edges that don't actually require any work. So there's a little more wasted work there too. But at least the work between threads is balanced. So finally, one thing we present here is just a more work efficient downward traversal, which would work, kind of as you expect in a queue. We assign a thread to only the vertex that's active. So for traversing from vertex 1, that's just vertex 1. And that thread will do its 3 edges. And then on the next iteration, we'll have 3 active vertices, 2, 3, and 4. And we'll assign a thread to each of those. So we still have the load imbalance issue because, here there's a thread assigned to vertex 4, and it does more work than vertex 2. But at least we don't have the wasted work. So it's not always going to be the best solution, but it often will be better than what we've seen in the past. So since it's not always the best solution, we kind of are motivated to find a hybrid method to figure out what the best solution is for a given point in time when processing the graph. So there's no one method of parallelization that works best. And in fact, you can figure out what type of graph quantitatively will work better with either the work efficient method, that third method I showed, or the edge parallel method, that second method I showed. And it turns out you only need to choose between those two. So that metric that I'll tell you which one of those two you want is called the diameter of the graph. So it turns out that's all you need to figure out. And the diameter of the graph is the measure of the longest shortest path that exists in the graph. So if let's think about this more constructively. Let's say you had a road network that was a graph of all the intersections. Intersections are nodes and roads are edges of all the streets in the continental US. Then the longest shortest path, or the diameter of that graph, would probably be from either somewhere in Washington to somewhere in South Florida, or somewhere in Maine to somewhere in Southern California, something like that, where it's like some very, whatever the longest path happens to be. So that's like one notion of how you can think of diameter. And for a graph like a road network, or something that's a little more regularly structured like that, you're going to have a very high diameter. There's going to be lots of intersections from South Florida to Washington. But you might think of like a social network, which is a completely different type of graph, and will have a much lower diameter because there are some people who are very famous who are connected to almost everybody. So all you have to do is hop from any person who might be on the edge of that graph to one of those really famous people, and then they can get to everybody in just very few hops. And that's kind of what I'm showing in this graph here. So what I'm showing in the plots in the middle of the slide here are the number of iterations, which you can think of as like the diameter from any given source, from 3 different source vertices. So in black, red, and blue, these are starting from 3 different source vertices. And on the y-axis, what you're seeing here is the size of the vertex frontier. So the number of active vertices for any current iteration of your breadth first search. And on the x-axis, you're showing the number of iterations. So for this mesh graph here on the left side, it's kind of like that road network where there's like a pretty good amount of iterations required to get from one side to the other. That's pretty consistent regardless of what source vertex you start from, although of course the size of any frontier will vary depending on where in the graph you are. But as you can see, any one frontier has less than 1% of the nodes in the entire graph. That's true for this middle section too, so it's a pretty similar graph. But on the right section, we have a randomly generated Kronecker graph, which is a scale-free graph. And in this case, it only has 5 hops to get from any one node to any other node for the 3 nodes that we chose to start from. But even though it has many fewer nodes, many fewer hops to get through from one side of the graph to the other, those frontiers are much larger. So we have up to 50 or 60% of the nodes in a single frontier, whereas here you see less than 1/4% or less than 1% for all the frontiers. So there's like 2 different types of like evolutions that we saw for a very diverse set of graphs. One that's high diameter, like A and B here, and one that's low diameter, like graph C here. And the conclusion we came up with was that for the high diameter graphs, you want to use the work efficient method that we came up with for this work, where you're only processing active vertices, because there are very few active vertices, and otherwise you'll be wasting a lot of work by processing all of them or all the edges or anything like that. However, with the graph on the right, you actually don't mind assigning threads to every edge, because so many of the edges are going to be active anyway that you actually want to just leverage the memory bandwidth of the GPU. So that's a pretty pivotal slide there. On top of this, you can even see that like maybe these first few iterations here, you actually don't have such a large vertex frontier. So maybe you want to switch off from starting with the work efficient method here and then going into the edge parallel method over here. And that's what we call the sampling approach. So the idea is that you can process some small number of vertices really fast, because each breadth first search is just order m time. And the problem with the all pair shortest path problem is that you're multiplying that by n breadth first searches. But you can estimate the diameter of all the graph's connected components by just doing a few of these really quickly, and you can store the maximum distance. And then you can have an estimated diameter from the median of those distances. Of course, if you have a connected graph, this is much simpler, but in general, it's you can make an estimate here, and that'll actually complete some useful work. You're basically doing pre-processing, but that pre-processing is actually computing parts of betweenness centrality scores. And then when you figured out, okay, well, my graph looks like this, so therefore I want to use the work efficient method, then you switch over to that method, and there's little cost of doing so. So you basically do like maybe 0.1% of the total work required by the algorithm to figure out which parallel method you want to use for the remaining 99.9%, and you get almost all the performance benefits from doing that, and you're able to figure this out all at runtime, which is really nice for any any type of graph. So let me just describe some results we had from this work. So this work was done, as I said, it's quite a while ago. So the GPUs here are going to look a little ancient, but what really matters is the relative improvement. But in particular here, we were using a CPU with Intel i7 2600K. The GPU is a GTX Titan for single node experiments. Has 14 streaming multiprocessors and 6 GB of memory. And then for multi-node experiments, we had slightly different GPU setup. We had Tesla M2090s, which were actually, I think, Fermi GPUs at the time, whereas the Titan was Kepler, and now we're all the way out to Maxwell, Ampere, and Volta. So these are slightly older generation GPUs. But what really matters here is that for the single node experiments, we had what at the time was like a very top of the line GPU, and then for the multi-node experiments, we had kind of decently top of the line, but not super top of the line GPUs. What's probably more important is the types of graphs that we do. So there's lots of times where I'm reviewing papers on graph algorithms, and I'll see that they test like 2 or 3 different graphs, or 5 different graphs, but they're all kind of similar. Like they're all based on some similar sort of matrix, or they're all based on some randomly some script that generates random graphs. But what we wanted here, and I think what you want in general when you're doing data science on especially graphs, you want a general sampling of all sorts of different types of graphs. So we have some notes here on what these are coming from. Some of these are randomly generated, some of these are mechanical models, some of these are social networks, some of these are for partitioning, some of these are internet, like I think routing instances. This is like a model of part of a Ferrari. So they're kind of all over the place. And what's really cool is you can look at the sparsity pattern to kind of see like how sparse the graph is and like where the connections in the graph are. So here it's like all very centralized. Here there's really not much at all except for like, neighboring nodes. And then here it's kind of all over the place because it's randomly generated. Anyway, so, the take home point from this slide is that we're testing all sorts of different types of graphs to really stress the algorithm and see what approach works best for what type of graph. Just like check my time real quick. Okay. So RGG is a random geometric graph. So in this case, we compare to the GPU fan package, and this is a log-log plot. So anything you're seeing that's linear is actually an exponential increase in time. So what I'm showing here is a randomly generated graph for 2 to the 15 vertices up to 2 to the 20 vertices, which is about 1 million. And then the time executed here is also logged just to make the graph a little cleaner. So what we can see is there's this massive gap. So we're going way faster. And unfortunately, the GPU fan wasn't able to scale past 2 to the 17 in terms of vertices for the graph because of memory issues. I think I mentioned before that we were able to not use this predecessor array, which made it easier for us to scale to larger graph instances. And we actually see that here. So this is like this is kind of like sparsity mesh of the graph too. So that's what that looks like. So here we're doing much better. We're beating it by 12x for all scales. And what we can see here is that there's like a similar amount of time to process a graph 4 times as large, which you would expect to take much, much longer. Del and A mesh is a different type of graph. It's very well structured, kind of a high diameter graph. So here the distinction isn't as large, but we see again that the GPU fan approach doesn't scale past like around 2 to the 17 vertices. But in this case, the edge parallel approach from GPU gems did work, at least past that. So down here, you can see like because we're using the sampling approach, we actually lose a couple of milliseconds and we're behind the red line, and our approach is the sampling approach in the black line. But when it really matters and we're dealing with graphs with millions of vertices, we're faster by a matter of days. So that's pretty important. So to look at things across the graphs that we tested, for road networks and meshes, we see a tremendous improvement. So the other algorithms were kind of targeted toward these scale-free networks. They weren't really targeted toward high diameter networks. So in one case, we took a graph that took 2.5 days to process, and now it just takes 5 hours, which is really incredible. So the work efficient approach is our new approach that we proposed. The hybrid approach is choosing one or the other based on the diameter, and the sampling approach is the runtime trick that figures out which one to do at runtime. Otherwise, for graphs that aren't road networks, we see kind of more modest improvements, some smaller improvements. But across this very diverse set of graphs, we're seeing 2.71x speed up over existing methods on average, which is really fantastic. Even better, I mentioned before that when we were making this decomposition of work to the streaming multiprocessor of the GPU, that each streaming multiprocessor was able to operate independently. Well, it turns out you can easily extend that concept to multiple GPUs, especially when the graphs are sufficiently large. And that's basically giving you essentially a larger bank of streaming multiprocessors to use, and a slightly more complicated reduction at the end of the algorithm to compile the scores together. But using MPI, that's actually not that bad. So what I'm showing here is on the y-axis, I'm showing the speed up of over 1 node, and on the x-axis, I'm showing the number of nodes we're using. So each shape here is for a different scale graph. So this is only like 1,000 vertices. This is like 4,000. This is 16,000, all the way up to 1 million. So we can see that as the graph becomes large enough, we're now supplying the GPUs with enough work to actually get linear speed up. So eventually, by the time we get to the point where we're processing 1 million vertices, we're able to distribute enough parallel work to 192 different GPUs, and we're actually able to traverse 10 billion edges per second across that cluster. And this scaling isn't unique to graph structure because it's taking advantage of the coarse grain parallelism, which is just dependent on the number of nodes in your graph. So there's a totally abundant amount of that. So as long as your graph is big enough, you can obtain linear speed up over 1 node with a cluster here, which is really, really good, strong scaling. So that was the main work that we presented at SC14. We also did some additional work for the more recent communications of the ACM research highlights paper that we were invited to present. So to improve on the work that we already have, we also come up with another method called cooperative parallelization. And this might be more similar to those of you who are like GPU computing experts out there. But you can use a cooperative warp-based approach where warps concurrently expand adjacency lists of vertices that are in the queue. where one warp in this case is 32 threads. That's just for the NVIDIA architectures. And this works really good for vertices with a high out degree, and has some, underutilization for vertices with low out degree. So in the picture, what I'm trying to show here is like, vertices 5 and 3 are active. So vertex 3, let's say that has a high out degree, at least in the picture, it's higher. Let's say that has enough threads for your entire warp to be active, whereas your next warp is going to process vertex 5, but it only has one edge, so only one of your 32 threads is actually active. So there's an issue there, but this works really well when you have scale-free networks where you have some vertices that have lots of neighbors. So to resolve the underutilization problem, we also can assign a thread to each enqueued vertex, and we use instead of a whole warp. So the difference between the last slide and this one is that we were assigning a whole warp of 32 threads, and we could instead assign just one thread if we know that the out degree of the vertex is particularly small. So in this case, vertex 3 is the vertex that has lots of edges, so we can assign a whole warp. And vertex 5 is one that only has like one edge, so we'll just assign a thread. And that way, so this is like warp 0. These are like 3 threads from warp 0, and this is 1 thread from warp 1. And that just makes it much more, it makes the load balancing much more efficient. So to show that, we have both the triangular mesh and a scale-free network to kind of go along the theme of before of trying to use both classes of graphs. And what we show here is in blue is the original edge parallel method. In red is our work efficient method. And in black is this new cooperative method. So the edge parallel method for something like a mesh we already knew would be pretty bad because it does lots of extra work. And then our work in the work efficient algorithm improves upon that by only enqueuing active vertices and only looking at those. So there's fewer threads that are not spinning and not doing work. And then the cooperative approach further improves on that by doing a better job of handling vertices with high out degree, even in the work efficient case. And then what's interesting here is that the blue and red lines are essentially swapped on the scale-free network, which makes sense because on the scale-free network, you have lots of edges that need to be processed at any given iteration. So the edge parallel method is better in that case because that's exactly what it's trying to do. It's trying to just feed a hungry GPU. Whereas the work efficient method is better asymptotically, but is not better at maximizing the memory bandwidth of the GPU for these types of graphs. But the cooperative method is kind of like the best of both worlds, where you can have your cake and eat it too, because it only enqueues necessary work and it's able to efficiently handle high vertex out degrees. So we compared this to a few different existing libraries. Galois, Ligra, and Gunrock are all very powerful libraries for doing parallel graph analysis. Galois came out of UT Austin, and I think it's still being actively developed. Ligra was out of Carnegie Mellon by Julian Shun, and Gunrock is out of UC Davis by Yangjia Wang, who's now at Google. And then hybrid BC is the last comparison. That's like my old method from the supercomputing paper. And what we're seeing is, versus my own method that was hybrid, we now have one cooperative approach that's better than both that you would have to choose from before. So that's 2.25x faster than that. And it's even more faster than all these other libraries because these libraries are a bit more generic. So we would expect to beat them a little more. But these are still supposed to be, very fast, heavily templated, optimized C++ for processing graphs on GPUs. So this is the average speed up over like the entire graph suite that I showed before. What's been nice about doing this work is that it's gotten some recognition. It was republished in Communications of the ACM. When it was originally put in supercomputing, it was nominated for Best Student Paper finalist. There were 7 finalists out of 83 accepted papers. We unfortunately did not win Best Student Paper because we lost to Machai Besta, and that's a bummer. But what makes him so special? Well, let's look at his website. All right, 2016 Best Paper HPDC, 2015 Fellowship, 2015 Best Paper Award, 2014 Best Student Paper, 2014. All right, this guy's pretty good. And in fact, I was looking at this slide just recently, and I actually went back to his website just to see like what he had done more recently, and it's still like stacks on stacks of best paper awards. So I'm kneeling Bachai here because I know him personally. He's a really good guy, but he's done phenomenal work. So if I had to take runner up to anybody in best student paper award, this is the guy you want to lose to. And now that I work at DE Shaw Research, I also have to acknowledge that there was another prize given out that year to DE Shaw Research for Anton 2. And now that I've joined them, I'm hoping we'll be able to get back on that stage for Anton 3 once that's completed. So in conclusion, GPUs are very useful for accelerating irregular and data-dependent algorithms, in addition to things that are more standard like matrix multiplication and machine learning algorithms. Cooperative and warp-based algorithms efficiently maximize the achieved memory bandwidth of the GPU. Using a system of 192 GPUs, we're able to traverse over 10 billion edges per second, and that scales linearly. So even if we had more GPUs, we could have done even better. And this cooperative approach improves on existing very high-tuned frameworks by anywhere from 3 to 7x. So with that, I'll stop there, and I'll be happy to take any questions. Thank you very much for listening.
Adam, thank you for a great talk. I should mention your work is appreciated because it led to an award that we received at New Jersey Institute of Technology, an NVAIL award from NVIDIA, which is the NVIDIA AI Laboratory Award. So you should take a little bit of credit for that.
That's awesome.
I'd like to invite anyone on the Zoom to ask questions through the Q&A in the chat. But maybe I'll ask you, Adam, your talk focused on Betweenness Centrality and really accelerating the speed. And as I mentioned with NVIDIA and GPUs, we've been using the Rapids AI toolkit, an open source data science toolkit to accelerate the data science operations that we have. And graph algorithms are included in that set. For data scientists on the call, could you give some examples of where Betweenness Centrality may be useful, how you'd use it with a data set?
So do you mean like where I would apply it?
Sure. So maybe give some examples of particular data sets and what it may find.
Sure. So you could think of a social network, and you'd be able, or like any sort of communication network, and you'd be able to find the people who are the best at spreading information. So who are the quote unquote gossipers in your network. So that might be one pretty interesting information that would be of interest to like the federal government or something. You could also think of, in this talk, we focused on, unweighted graphs for simplicity, but you could also imagine weighted graphs, and you could follow like financial transactions, if that would be of interest. You could also, it's really like, the question is really, what can your graph represent? And that's kind of the power of these sorts of algorithms, is as long as your graph can represent the data, then the algorithm will figure that out for you. But in general, yeah, it's meant for finding like a ranking of like the most influential pieces of your network. So if you have like a routing or computing network, and you have some way of measuring like latency from links to another, you could find the links that are most problematic, and maybe those are the ones you need to fix and switch out if you're like in the IT industry or something like that. But the applications are really myriad.
Thank you. Now that you're working at DE Shaw Research, do you have any insights for a research career and how your training has helped you do what you do today?
Oh man, yeah, I think it's hard to even start there, but yes, I definitely do have a few things I could say. I think that being a grad student can be pretty stressful at times, and it can be pretty discouraging. And one thing I always kind of did is that, like, when I couldn't find answers to things, I would always try and appreciate the questions. So grad school is a time in your life where you're really able to study things pretty freely, and to some extent, of course, and be able to really work hard on like a single individual project that you're really passionate about. And I would definitely take advantage of that time and really appreciate it, because that might not be the case after you graduate. Although I'm not saying that for personal, I love my job, don't get me wrong, but to be able to like work on whatever you want is a rare opportunity. I also would I would recommend people take internships. I'm very big on those. I did quite a few of them when I was a graduate student. Um, they get you better industry connections. They can connect you to future internships or future job offers. They're a really fantastic opportunity to get to know people in the industry and meet more people at conferences, to grow your network, and to just get valuable experience in an industrial setting where you might have like, more rigid software techniques than you might in an academic lab.
Thank you. I see that we have a question in from Ashish. Nice work in presentation. Can we categorize the Betweenness Centrality for different events and process that at the same time, or would it go in iterations?
So I'm not sure if the question's referring to parallel computation within Betweenness Centrality, or if it's referring to what you might call like a time multiplex Betweenness Centrality. So I'll just try to answer both real quick. So the point of these algorithms is to take one static snapshot of a graph and to process that in parallel very fast. So in that case, you're parallelizing across elements. Another thing you could do, and this is still a pretty hot topic of research, is to take what you could consider a dynamic graph or a graph that changes over time and try and process that. That's not something that we looked a little bit into that. We did have one MTAP paper on an approach to doing this, but I think there's a lot more work there. That's a much more difficult problem because when your graph is changing over time, the algorithms become a lot more complicated.
I think there's some work with Oded Green on looking at dynamic Betweenness Centrality. I think
that's
he
right.
had some interesting results there.
Yeah.
So I know that you like concerts and comedy. Can you remember the last concert you've seen?
Yes, it was right before the pandemic started. So actually, the last real like social night I had was actually a celebration for my birthday. My birthday is in February, it's mid-February, but we celebrated like early March, and it was like the last day where people like, at least I'm in New York City, so it's the last day where people here really went out. So we went to like a live band karaoke show. So I don't know if that counts, but we.
That's great.
Yeah.
So Pantelis has asked a question. Thanks for the presentation. What is the connection of graph algorithms such as this and GNNs, if any?
GNNs being neural networks?
Yeah, graph neural.
So there's one, I don't know about this particular algorithm, but in general, one thing that's a connection is that you could look at any sort of graph problem as like an isomorphism of a matrix problem. So I'm not a machine learning expert, but there's something called the graph gloss, which basically tries to take like graph algorithms and recast them as matrix problems because one, it's a little simpler to understand, but two, it's much more computationally efficient to do matrix multiply than basically anything on a computer. And this is especially useful for dense graphs. So I think the GNN approach would also take advantage of some similar algebraic techniques there. So I think there's a connection there.
Okay. Thank you.
So Adam, I know that you come from an architecture background. Can you speak a little bit to how knowing the architectures have helped you design algorithms for data science, and also maybe talk a little bit about new architectures you think are interesting for those in data science?
Sure, yeah. I think, so there's obviously different levels of abstraction when it comes to this sort of thing. I was obviously pretty low level, but there are people lower level than me for sure. So I enjoy kind of like hardware aware programming, and that's like, you need to know like the different types of architectural paths that are allowed and all sort of thing. And there's even this whole notion of hardware software co-design. So for where I work now, for instance, at DHL Research, we work on molecular dynamics, and we have direct feedback from our embedded software engineers who are working on the latest and greatest molecular dynamics techniques to our hardware engineers to figure out how to fit that in a computational pipeline. And not everything is practical for hardware, but it's really interesting to see those conversations flow back and forth. So I think it's it would behoove anybody to know more about the architecture they're trying to program on. But of course, not everybody wants to work at that low level, so you kind of have to find where you're comfortable. Some data scientists, might not ever care too much about the hardware, and that's okay if the algorithms they're trying to do aren't supposed to be, you know, very high performance. There's still plenty of useful work you can do, and not everything needs to be like you know, super tuned. As far as interesting architectures go, I mean, other than GPUs, I haven't had the chance to play with many other than Anton. And Anton's interesting. I've done some embedded software for tests, but you know, you can think of it as this very highly parallel computer that is only meant for doing molecular dynamics, but you know, it does have some somewhat general purpose cores on it, so you can do lots of other things too. So you know, the concepts I learned from GPU computing really, and just parallel computing, really carried over easily there, which was really nice. I think that you know, knowing things like the bandwidth of like different paths is really helpful. So, you know, you might have to send data from one architectural component to another, and there might be like some easy path that's there to program, but there might be some like alternative path for whatever reason that's like more high performance, but like maybe, you know, slightly more difficult to deal with. And like, that's always a trade-off I'm kind of constantly making in my day-to-day work now.
So thank you, Adam, for a great talk. I'm also really looking forward to seeing Anton 3 come out. That's exciting. I'm glad you're working on it, and hopefully we see some great results soon. So thank you again. I'd like to remind everyone here on Zoom and YouTube Live, subscribe to our channel on YouTube, follow us on Eventbrite, and we'll see everyone again a week from today, next Wednesday, for the next talk. Thank you, everyone.
Thanks a lot, David.